Or Cynthia, did that work? Do you have audio now? Okay. Okay. So any suggestions on what you want to do first to determine the height of this tree? Find which angles? There's lots of angles.
I would find the other half of the angle on 35 degrees. Find that
supplement. Angle. That's the
yeah.
word you were looking for there. Was the
Thank you.
Of that 135. What is the supplement of the 135? 145? Okay. So that's good. That gives us a chance to find this other little tiny angle up here, right? That other little angle has to be 2 degrees. And we haven't even used any of our big tools yet. Yeah. And we could presumably say that if we did drop that altitude down, that we could say that this other angle here, I'm not sure if we care, but we could certainly say that that other angle is the complement of the 35, which would be what, 55. So we could say that that's a 55 if I wanted to write it in there somewhere, but I don't think we're actually going to use that. But it certainly is an angle that we know. Actually, that pink shows up pretty well on that black. So yeah, we can actually determine all of those angles without using any big tools. Okay. What do you want to do next?
Finding the sides of the tree, like how tall the tree is, the sides.
By doing what?
Well,
let's, just in case it helps, let's label some of these. Let's call this length A, this length B, then this length C, and this, because it's the height of the tree, I'm going to go ahead and call that H. So our goal is to find H, right?
Uh-huh.
But what are we going to have to find next? Unless we've got some way to find H now.
No. You're gonna have to find well, it says the feet of the 100 feet, like the from the angle
Mm-hmm.
to the side is 100, and that is C. So that's like what it has to equal, right?
Well, that's
Well, it doesn't really matter, right?
that's the distance from here to here.
Mhm.
That's not the distance. We don't know this distance.
Oh, okay.
If we knew that distance, we'd only need one angle and we'd have a nice right triangle, right?
Yep.
So the reason we're having to use this big tool is we don't know how far away we are from the object. And that's one of the reasons we use this kind of stuff to, tell how high is this mountain we're standing over here. Well, if we wanted to use a right triangle, we'd have to know how far are we from the base underneath that high peak. We're not going to know how far that is, right?
No.
We could say measure to here, but this is all underground. We don't know that. Or if it's a star or a satellite or a planet or something, and we're down here on our little planet trying to measure it, there is no right triangle distance to find there. Fair?
Yep.
So this is kind of we either don't know how far we are away or don't want to go to the work of finding that distance because it's a deep dark forest, and deep dark forests are scary. We can take our measurements over here and still find all these things. So,
is it possible that we can do like the reciprocal of 100 of the 2 degrees? Like that would be sine, right? Because it's opposite.
The reciprocal of the 2 degrees?
Of like the 2 degree sine.
Okay, use law of sines.
Yeah,
the 2 degrees and the 100, because those are opposite. Okay.
Yes.
You certainly do know, you're absolutely right, that
the that's 100, what I meant. Sorry.
That's okay. That 100 in ratio to the sine of the 2 degrees, that is an opposite pair that we know. In the little triangle, because we do have this kind of little triangle here, right? Fair?
Yes.
So in that little triangle, we do know that ratio is going to allow us to use law of sines. What do you want to do with that ratio?
To find the long side, right, first, then finding like the smaller size.
Actually, whichever one you want.
Whichever one. Okay.
Which one you want?
Then we can do. Are we still allowed to use sine, or do we have to switch to cosine?
As long as we have an opposite pair, we can use law of sines.
Law of sines.
Since
Okay.
you've identified your opposite pair, so we can stick with sine.
Okay. Okay, then I would do I can do 140. Well, yeah, 145 degrees.
And the sine of the 145 degrees.
Sine of 145 degrees, and then A, because it's the opposite.
Yeah. In V and K, you guys happy with that?
I would go about the same method, but I would use to find line B as opposed to, because line B is what we really need.
Either one actually works. Kind of depends on how you see it, but both are perfectly valid. So sine of the 33 degrees. So RA is the 100 sine 145 degrees divided by sine 2 degrees. So why don't you guys let me know a nice approximation for that? And our B would be 100 sine 33 degrees over the sine of 2 degrees. So Cynthia, since you liked B, why don't you give me a decimal approximation for B? And Beatrice, if you can give me a decimal approximation for A, that'd be great. And Kate, if you want to check either or both of those, just to make sure we're headed in the right direction.
So how come you're allowed to use the reciprocal of those? Because I would have done, like if you were finding B, I would have done sine of 2 over 100.
Actually, one of the nice things about the law of sines, if you know that A over B is equal to C over D, if two ratios are equal, then the reciprocal of them will be equal.
Okay.
So you can actually use the law of sines in either orientation, with the lengths on top or with the angles on top.
Okay.
So generally, if I'm trying to find a side length, I put the side lengths on top because it's easier to solve. If I want to find the angles, I'll put the angles on top with the sine, because then it's easier to solve.
Got it.
But they all have to be that way. You can't have one way and the other way. Fair?
Okay.
So it just makes it a little bit.
Okay, approximation for B is 1,560.6.
1,560.6.
Yes, 0.6.
That's feet. Okay.
And for A, I got 1,643.5.
And those should be similar in length, and they are. A should have been longer, and it is. And scale-wise, I mean, that's a lot more than our 100, but it's way projected out there, right? So those numbers seem reasonable in scale. Okay. As I said, we actually only need one of these, and it actually doesn't matter which one we have. They both should work. This diagram we started with, how many triangles are in this diagram that we started with?
2, 3, 2.
3. There's the little triangle that's now green. There's the medium triangle, this kind of medium-sized triangle. And then there's the really big, the whole thing triangle, right? Where, you know, the green one is in the middle of that. So if all you had was length A, you can use the big triangle because it's now a right triangle. If you had side B, you could use the medium triangle. But to get either of those, we needed the little triangle. Okay. So we don't really need both A and B, but we could use either. Just to continue with the A that we started with, oops, or to erase it. Yeah. Can we use A to find this nice height? Do we need law of sines or law of cosines?
I would say law of sines because we have 2 angles and a side.
Anybody want to argue with that? I want to argue with that. I wouldn't use law of sines.
I kind of want to argue with myself about that.
How so?
Because you can find law of, use law of cosines for it. Because you have one angle and a side.
A lot of cosines, we really need two sides. So I'd argue against law of cosines as well. What kind of triangle is this big triangle? It's a right triangle, right? If it's a right triangle, we don't need law of sines or law of cosines. Our basic trig functions can handle right triangles, right? So we don't need the big guns. Law of sines and law of cosines are adaptations to non-right triangles. As soon as we find out that 1643 is a hypotenuse.
Mm-hmm.
We have a hypotenuse. We want an opposite length. That's just a straight, good old everyday sine question. So I don't disagree with you that you can use the law of sines. I disagree that we should use the law of sines. Is that fair? Beatrice, Cade, Thompson, you guys good with that logic?
Yes.
Yes.
Cool. And one of the things that often happens is because law, particularly law of sines, is so nice, people end up wanting to use it everywhere. And oftentimes they just use tangent. We don't need that. You know, if you got a right triangle, just use the right triangle. So 164.3.5 times the sine of 33 degrees. Got a value for that distance?
Yes, I got 895.1.
195.1. That's feet.
Feet, yeah.
Okay. Now, why did I call that D instead of H? Well, just to be picky here, that's this distance above our eye line, but our eye line is another 6 feet. So how high is our tree? $901.1 feet. Now, again, fun part, Cynthia, you said you wanted to find B instead. Okay, that's fine. We'd still, have this length then, the 1560.6. So that would mean the sine of this 35-degree angle in there would have to be equal to that distance over 1560.6. So that distance then should be equal to 1560.6 times the sine of 35 degrees. And hopefully that should also equal about 895.1. Oh, good. I always worry. So either one would have worked just fine. We don't need both. Any questions about that problem?
No, it makes sense. Hmm.
So let's see. What else could we survey? I like my little surveyors. Oregon, by the way, last year they were, I don't know, and they probably still are, the last several years, the state of Oregon has been really low on surveyors, and they've been hiring surveyors like crazy. It's one of those fairly nice jobs that people kind of don't know exist anymore. So we've got a lake, say, and we are tasked with figuring out about how big is this lake. Now we could get a satellite picture of it and measure it really accurately, but you have to have satellite time for that, and that's kind of irritating. Actually, with Google now, that's easier. But if we want to send a surveyor out there to get a good approximation of how big this lake is, that observer can drive out or hike up and get to some point near that lake. And a nice way to approximate it is to get kind of take some measurements here. So particularly with lasers nowadays, you can go from this one location and figure out approximately how long to some object over here. See, there's some tree or some rock or some object over here. So you bounce a laser off of that and you figure out this is 1,528 feet. And then you bounce the laser off some object over here and you find out that this is 1,281 feet, roughly. Since you're standing here, you can certainly measure the angle between those two observations. Let's say the angle between those two observations is 42.5 degrees. Well, this should be enough information for us to figure out not only how far is it between these two observations, distance. So we can calculate that distance and any of those other angles if we care. Again, this is a nice way to do things like figure out how far apart stellar objects are. You want to know how far apart is that star from that star, or that asteroid from that moon, or whatever. We can use the techniques from the first problem we did to find distances from the objects. So to find that 1528 and 1281, and then use this technique to figure out how far apart those two stellar objects are. Or you can do the same thing on this atomic scale. So, these techniques run the gambit. Anyway, so we should be able to figure out that length, and using that, we can end up finding the area of that triangle, which can approximate the area of the lake. I mean, some of the lake is outside that triangle. Some of the lake is, there's some earth inside that triangle, but, depending on how accurately we take these measurements, we can get a more or less accurate area of the lake. And the lake is going to change size during the year anyway. So we're just trying to get an approximation, right? So let me give you, say, 4 minutes to figure out that distance D and start trying to figure out how you'd want to find that area. I want to talk about some tricks for area. went with that tool. Huh? It's not a bad tool. Yeah, 4 minutes is such a long time when you're having to sit and wait quietly.
I'm confused, even though I think I did a problem like this yesterday.
Well, it's one of the reasons I wanted to talk through them, you know? I know you guys have been playing with this stuff, but I think it is helpful for us to look at. So first thing I do want to find, though, whether we need it or not to find the area is a question, but just to be able to find that length D, what tool do you want to use to find that length D?
I use law of cosines for that.
We don't have an opposite pair anywhere in this triangle. So to build this opposite pair between D and the 42.5 degrees, law of cosines is a nice choice. So law of cosines. So law of cosines says that the square of that length D should be equal to the 1528 squared plus the 1281 squared, like it would be for Pythagorean theorem, but since it's not a right triangle, we've got to adjust, and that's what law of cosines does. So minus the 2 times the 1528 and the 1281 times the cosine of the angle between them, the 42.5. And that ends up with some obnoxiously large value. I don't know what that obnoxiously large value is. Do you guys have that obnoxiously large value? No. I'm just going to say a big number then. And we take its square root. And hopefully you guys can give me that approximation, if I'm patient enough.
I'm getting 1043.79.
So is it okay if I go 0.8?
Yeah.
Cool. And that seems reasonable. It's in the scale of the other values, but it's, that 42 is probably the smallest angle in that triangle. So that being the smallest of those 3 side lengths is very appropriate. So I think that sounds like a good number. Okay, so if we wanted to know the distance between those 2 objects, or that distance kind of across this side of the lake, then great, we know that. Okay, did that work so far?
Yes.
Cool. But if we want to find area, we have to make some choices. For area, we have a couple of different tools to find area. Generally, when you ask people what is the area of a triangle, the kind of, knee-jerk response, if you remember area of a triangle, is 1/2 base times height. And that's a perfectly reasonable area formula. It just has one particular problem, and that's the whole base and height issue. Base and height, by definition, are perpendicular pieces. So if that's a base, the height isn't one of the other sides. The height is referred to as the altitude of that triangle. So to use this base, a 1/2 base times height formula for the area of a triangle, we'd either have to calculate that height or use some different tool. And this has always made the whole half base times height formula a little bit problematic, because if you're doing something, even if somebody just gives you a triangle and says, find this thing's area, you can measure the side lengths pretty easily with a ruler, but trying to measure that height exactly perpendicular to that base is often a little bit of a chore. So we have a couple options. What options do you guys know of? This is often one of those, did you do the reading questions? You guys are going to be quiet today. Well, option 1 goes back a little more than 2,000 years, or around 2,000 years. In the 1st century AD, Heron, often just called Heron nowadays, but it's Heron, of Alexandretta, developed what is commonly referred to as Heron's formula. Also credited with building the first steam engine, by the way, though it wasn't used for anything other than entertainment. Anyway, Heron's formula is an attempt to have a different way of finding area that's a little more convenient. Unfortunately, Heron's formula is a little bit of a pain. Heron's formula defines a value S that is the half perimeter. So you add the 3 sides together, find the perimeter, divide that by 2. So you get this half perimeter. And then you multiply that half perimeter by the difference between the half perimeter and each side. Yeah, Greeks, I tell you. And then you take that thing's square root, and that square root is supposed to be area. Don't use that. You can use it. It works. It's fine. It's just a little bit of a pain. Fair? Now, yeah, 2,000 years ago, it was awesome. People were like, this is the best thing ever. Let's buy Heron a cup of coffee and shake his hand. But we have better tools now, right? If you looked at your derivation of law of sines, that derivation of law of sines, part of it was calculating or writing a formula for that height based on this angle. So if we know this angle, I'm going to call it A, and let's say this angle is C, so that's length C. Then if we focus on this little triangle here, that height is equal to, well, the sine of A. Well, the sine of A is actually H over C, but if we multiply both sides by C, that height is equal to C sine A. Fair? And the way we built law of sines is you then do that with the other angle, and you get those 2 ratios that you can set equal to each other, and you build law of sines. But this gives us a formula for this base, not for the base, sorry, we already have a base. It gives us a formula for that height in our area formula. So in a lot of ways, a better area of a triangle formula is 1/2 base times height, where height is the C sine A. Now, you'll often see this formula written with any, you could say it's 1/2 AB sine C or 1/2 CA sine B. It doesn't matter as long as these two lengths are the lengths that make up that angle. Fair? Well, and that's actually the information we started with. We have the two lengths, these two lengths, and the angle between them. So while we could use Heron's formula, it does work. I've derived Heron's formula from the geometry. It is horrendously complicated thing to build and kind of an annoying thing to even just use, particularly since in most modern applications, finding that angle and using the trig is a lot easier. They didn't have those tools in the 1st century AD, so Heron's formula is great. But frankly, even if we knew all the sides, I'd find the angle and use this thing. So area of a triangle being 1/2 AB sine C is a really, really good formula for area of a triangle. And you should kind of either replace or sit next to 1/2 base times height in your head. Fair? Where Heron's formula or Heron's formula is just kind of a neat tool that's fun at parties. I don't know what kind of parties you guys go to. But. So if we wanted to find this area, 1/2 of the 1528 times the 1281 times the sine of 42.5 will give us a nice value for that area, which should equal what you would get from Heron's formula, but not be as tedious. Can anybody find that value for us?
It's about the same.
Yeah, up to the approximations of the 42.5 and the 1281 and the 1528 are rounded, so it's going to be, if you keep all the decimals all the way through, it'll equal. But
Yeah.
So what is it?
661 189.3268.
How about 3.3? So 600,000 some odd. Cool.
And that was basically what it was using Heron's formula as well.
A lot nicer, right?
A lot easier.
I remember I gave a question once on a test. It didn't ask for this distance. It just said, hey, here are these lengths. Here's this angle. What's the area of that triangle? And the intention of the problem was to do this, because that's what it takes to find that area. But about, I think 2/3 of the students did all of this. They used law of cosines to find that other length, which is fine, and then grabbed Heron's formula and did all the calculations for Heron's formula to find the same area. And I was like, that was not supposed to be a 10-minute question. It's supposed to be a 2-minute question. So they were all, this test was so long, only because you made it long, you know. So it is one of those, which tool is going to be more efficient? And as I said before, even if you're given just the lengths, if somebody said, hey, that's 5, that's 8, and that's 7, find this thing's area. Okay, Heron's formula is a great formula. Use Heron's formula for that. But a little bit of law of cosines to find that angle, and then 1/2 of 8 times 7 times the sine of that angle, and you're done. I'd still be tempted to just use 1/2 AB sine theta. Even given the kind of the nicest setup for Heron's formula, I would still probably use 1/2 AB sine theta. For those of you going into calculus and physics, the 1/2 AB sine theta becomes a very common triangle tool, especially calculus. So your book de-emphasizes this formula a lot. While it's building law of science, it kind of goes, hey, and that means here's a formula for area, neat. And then it kind of just drops it. But I wanted to emphasize it for you because it is a really handy formula as your career goes along. So Cade, was that all helpful? You said you did these, but they were a little bit weird.
Yes, it makes a lot more sense now.
Cool. I don't want to badmouth Heron's formula. Heron's formula is awesome. And particularly Heron's formula being developed in the 1st century. You know, some of the things developed by Heron. And that's one of the few things that was credited to a Greek mathematician that even now we still credit to a Greek mathematician. A lot of the things we used to credit to Greek mathematicians were actually from Persia or India or somewhere else. But Heron's work has stayed with no other evidence of it being developed previously anywhere else, as opposed to things like Pythagoras. Almost all Pythagoras' work was from Persia, India, or Egypt. And we often just name theorems and stuff after the first person who wrote it in a book that we can find. So that's one of the reasons a lot of things are attributed to the Greeks. Anyway, questions about either of those? Okay, I think that homework assignment's due, what, Friday? 838-182, sorry. Yeah, 182 due Friday. Monday and Wednesday, we'll talk about 8.3. Yeah, I think it was due tonight, but I moved it just to give you guys a little bit more time on Monday. But just because there were a fair amount of people who hadn't started 8.2 yet, and I just want to make sure you guys had time to work on that because they are, some super, super powerful tools. But 8.3 is on vectors. 8.3 is only one section, but there's a tremendous amount of stuff in that section. So make sure before Monday, you start looking through that 8.3, maybe watch, go online and look at vectors and maybe watch a YouTube video on vectors to get yourself kind of prepped for those ideas about vectors. Vectors, for those of you, again, going on in any physics or mathematics or engineering or chemistry or lots of types of finance or lots of things. Everything starts being done, well, not everything, but a tremendous amount of things end up being done in the language of vectors after this course. So, it is one section on, hey, here's what vectors are, but there's a tremendous amount of information in that, and it's all super duper important. But the nice thing is, with all the tools that you guys have built up, it's actually a pretty mechanically pretty easy section. It's just kind of a lot of perspective and different vocabulary. So make sure you look that over. Is there anything else I can do for you guys today before you trundle off? I know we only did a couple problems today, but hopefully they were good problems and cleared up some good stuff. So anything you guys need?
No, that was helpful. Thank you.
Sure.
Nope, all good. Thank you.
Awesome. Okay, I'll talk to you guys later. Have a good day.
I have a question real
You
quick.
too.
Yes, ma'am.
Can you scroll to the first example that you did for sign? Okay, I just want to take a quick are you gonna upload these videos on the
Yes.
okay. Okay. And it made sense. I was kind of having trouble with laws of cosines. Like now that I see it, I believe that it's a little bit more easier than laws of sines. Now that I see it, but it was kind of getting difficult for me.
Which one? Yeah, some people like law of sines better. Some people like law of cosines better. Law of sines has the advantage that it's small,
Yeah, it's small. Yeah.
but it's used in so many different ways
Mm-hmm.
that in some ways because it's more flexible, it's got more options of how it's used. So sometimes it's used in more complicated scenarios. Where law of cosines, it's a bigger formula.
Yeah.
It's kind of a more intimidating formula, and you end up having to do a fair amount of little calculations in it. But it really does one job.
Mm-hmm.
So in some ways, yeah, that's a little simpler, because if you're using law of cosines, you're either finding that side or finding that angle, and that's it. So, which one's a nicer formula tends to be kind of, up to an opinion.
Yeah.
But together they form a really powerful team.
Yep. Yeah, I agree. Yeah, for sure. Yeah, that's all what I had. And yeah, it makes sense so far.
Okay.
Yeah. All right. Thank you. Have a good day.
You too.